Hello everyone, welcome to my class. Today I am going to cover Green's theorem. First, let me give you a quick preview. The Green's theorem is another big theorem of vector calculus. It connects a line integrals of a vector field over a simple closed curve C and a double integral of a function over the plane regions D enclosed by that curve C. First definitions. Let me scroll down. A positive orientation of a simple closed curve C enclosing a region D means as we walk along the curve, the region D is always be on our left. So that means the positive orientation of a simple closed curve C refers to a single counterclockwise traversal of C. Okay, great. Next, let me state the Green's theorem. Let me scroll down. The Green's theorem says, that's better. Green's theorem says, let C be a positively oriented simple closed curve in the plane and D be the regions bounded by C if vector field F with component PQ is a vector field in R2, then the line integrals of a vector field over the boundary, which is this is same as the P dx plus Q dy over the boundary C. This is again a line integral in differential form, equals to the double integrals of Q partial derivative with respect to x minus P partial derivative with respect to y times dA. dA is the area element. So this theorem says instead of computing line integrals along the boundary, we just compute the double integrals inside the region D bounded by that curve C. Awesome. Now let me make a quick point here. Here our vector field is not conservative. If vector field is conservative, then the line integrals over the closed curve will be 0. Okay, now let's apply Green's theorem to compute the line integrals. So I think let me go a little bit down here. So use Green's theorem to evaluate the line integrals f dot dr over C, where f has component xy comma x square y cubed. So this is the P, this is the Q, are the components of vector field, and C is the triangle with the vertices 0, 0, 1, 0, 1, 0, and 1, 2. Great. So to compute the line integral without Green's theorem, we have to compute this line integral. Our C is the union of this side, so another side and another side. We have to compute the line integral along these three curves. But using Green's theorem, instead of computing the line integral along the boundary, we compute the double integral inside the region bounded by that curve. Awesome. So here's the formula. Line integrals of f over the boundary equals to double integrals of the partial derivative of q with respect to x minus partial derivative of p with respect to y times dx. So now let's start. What's my p? P is xy. Take partial derivative of p with respect to y. X is constant. Take partial derivative of q with respect to x. The y cubed is constant, so simply 2xy cubed. And here is a domain. So let's describe this domain as vertically simple. So draw a vertical slice, then the y limits, that's better, y limits is given by the x-axis, so y equals to 0 is our lower bound for y, and for the upper bounds for y is this line. This line is simply y equals to 2x. We can easily find this equation of this line. One point is 0, 0, another point is 1, 2. So the equation of a line joining 2 points is y minus y1 equals to y2 minus y1 over x2 minus x1 times x minus x1. So So x1 y1 is 0 0, x2 y2 is 1 2, and simplify. This gives you this diagonal line y equals to 2x. So the upper limit of y is y equals to 2x. And for the x bounds, x equals to 0 2, x equals to 1. So we have the limit for our double integrals. And now put qx equals to 2xy cubed, put py equals to x, use those limits and evaluate the double integrals. Let me scroll down here. So the line integrals of f over c equals to double integrals. This is qx, this is py, qx minus py times dA. dA is dy dx in our description of domain. Y bound 0 to 2x, x bound 0 to 1. Integrate first with respect to y, so x is constant. Write down the x integral as it is. Then this becomes, with respect to y integrals, 2x y to the power 4 over 4 minus x times y, and put y limit, y equals 0 to 2x times dx. Now better, put y equals to upper limit minus y equals to lower limit. Lower limit gives you 0 everything, so put y equals to upper limit 0 to 1 and simplify. This gives you this expression. Integrate with respect to x and put the value x equals 0 to 1 and simplify. Just a routine computation. This gives you 2/3. Awesome. So we found the line integrals in example 1 as 2/3. Now let's move on. Let's do example 2. Evaluate the line integrals where line integral is given as I equals to line integral over c of y plus e to the radical x times dx plus 2x plus cosine y square times dy. You may be thinking here how to integrate out this e to the radical x and cosine y square, but we have the Green's theorem in a rescue. So where this C is boundary of the region enclosed by two parabolas given by y equals to x square, x equals to y square. So again, using Green's theorem, instead of computing line integrals, we compute the double integrals inside the domain or regions bounded by the curve. So let's draw these parabolas here. So y equals to x square is this parabola, x equals to y square is this parabola. Solve these two equations. They intersect at 1 1, and we can, let's talk about limit here. Then we can describe the domain as vertically simple. So entering value of y is given by this lower curve, which is y equals to x square, y equals to x square. Then upper values or upper boundary of y is given by this curve, which is x equals to y square. Solve for y equals to radical x, so that's the upper bound for y, and for x 0 to 1. Now let's go to this other side, to the left side here. So what is my p here? My p is y plus e to the radical x, q is 2x plus cosine y square. Then take a partial derivative p with respect to y. Wow, this disappears. Only 1. Partial derivative y with respect to y is 1. And partial derivative q with respect to x is simply 2. This one again disappears, 0. So now we have this constant here. Then let me scroll down. What the Green's theorem says? Green's theorem says line integral equals to the double integrals, and this is qx minus py. qx2 minus py is 1 times dy dx, y integrals inner integrals, x integrals outer integral, with y limits here, x squared to radical x and x limits 0 to 1. And solve for or evaluate for this integral first with respect to y. So write down the x integral as it is. 2 minus 1 is 1. This is constant, pull outside. Then integration of dy with respect to y becomes simply y. Put y equals to upper limit minus lower limit, which is here, radical x minus x square times dx. Then integrate with respect to x and put the value x equals to 0 to 1 and simplify. This gives you 1/3. So we found the line integrals of example 2 as 1/3. Now let's move on. I have a quick remark. The Green's theorem can also be used to compute the area of a closed region bounded by the curve by this formula. So we talk about this formula here. This is the notation for area of the domain or the region D bounded by C. So AD equals to, this is the Dahal integrals to find the area, integrand function is 1dA. So this part is just the formula. Then there is a trick here. 1 equals to 1/2 times 2. 1 minus 1, 2. We just write as a trick here because I'm comparing right side to the right side of our Green's theorem and come up with a nice area formula in terms of line integral. Okay, that's the idea here. So then comparing the right side to the right side of Green's theorem, this is qx, this is py. Then how to extract p and q? Integrate qx with respect to x, so gives us q equals to x. Integrate py with respect to y gives us p equals to minus y. Then looking at the Green's theorem's right side, write down the left side, so 1/2 as it is. Then line integrals, this is p dx plus q dy, p q. So now we have the formula of area of region bounded by the closed curve C is 1/2. Single integral means line integrals over the closed curve C, x dy minus y dx. Awesome. Let's use this formula and do one quick example. Example 3. Find the, let me scroll down. That's better. Find the area of the disk enclosed by the circle of radius a. Means we are finding the area of the circle, which is pi radius square. So let's verify that result using Green's theorem. So in parametric form, the disk equation is x equals to a cosine t, y equals to a sine t, t between 0 and 2 pi. Take x derivative, which is dx equals to minus a sine t dt, derivative of y dy equals to a cosine t dt. Then use the formula here. What is our formula? Our formula is minus y dx. So area equals to 1/2 in single integral, which is a line integral, 0 to 2 pi. Then start from negative y dx. Start from negative y dx. So negative y is a sine t, dx is minus a sine t dt, plus x a cosine t, then dy a cosine t dt. 1/2 as it is, integral 0 to 2 pi as it is, multiply a square sine square t plus a square cosine square t, pull a square out, sine square t plus cosine square t gives you 1, just simply a square dt. A square constant, pull outside, integral of dt is simply t equals to upper limit 2 pi, cancel 2, this is simply pi a square. So yep, so we found the area using Green's theorem. Great. So this ends these sections. In our next sections, we cover curl and divergence. Thank you.